In the late 1990s, Google stepped onto the scene to address a rapidly growing problem. With the ever-growing popularity of the internet, how does one sort through all that information? How does one quickly and easily find what they're looking for? While there were many trying to address this problem, Google was the best and has remained so for nearly 25 years. In much the same way that Google provided a solution to this problem for the internet, the Graph is looking to provide the same solution for blockchains. Welcome to Crypto Sketch 101. We're the #1 go-to spot for all things crypto, and we're glad you've stopped by. If you love cryptos as much as we do, please give this video a like, and be sure to subscribe to our channel. In today's video, we'll examine everything you need to know about the Graph. We'll take a close look at what problems it's trying to solve, some of its unique components, and even take a look at a use case example. There's a lot to cover, so let's get into it. Imagine for a moment that you've got 3 books in front of you, each of them written on the topic of Ethereum. You're looking for information relating to Ethereum's gas fees, so you decide to check the indexes to quickly find what you're looking for. You open up the first book and find that it has no index. You open up the second and third book and find that they have no indexes either. You're left with having to flip through the books to find the piece of information that you're looking for, and in the worst-case scenario, may have to resort to examining each of them page by page. It would be much simpler if each of them had an index that you could reference to quickly and easily find information pertaining to gas fees. Now, imagine applying the same scenario to blockchains. Imagine you are looking for information on a particular transaction. Without an indexing tool, you would have to go block by block examining each one for the particular transaction. In the case of Ethereum, there are currently almost 15.5 million blocks, with an average of around 6,300 new ones being created each day. Indexing reduces the amount of time and effort that is needed to find information. In much the same way that Google brought indexing to the internet and web pages, the Graph hopes to bring indexing to blockchains, starting with Ethereum. In a nutshell, the Graph is an open-source indexing protocol for blockchain data. It simplifies information retrieval from blockchains to make smart contract and decentralized app development easier. While there are a few alternatives such as Etherscan that provide a similar service, the Graph is the first to be fully decentralized. As such, it does not have exposure to the types of vulnerabilities associated with centralized solutions. In order to better understand the Graph, it helps to understand a few key terms. The first of these is API. In computer terminology, API stands for Application Programming Interface and is a way for 2 or more computer programs to communicate with each other. It is essentially the transfer of data behind the scenes. The API takes requests, tells the system what you want to do, and then returns the response back to you. API operates in the blockchain world as well, helping individuals interact with exchanges or 2 or more applications to interact with each other. The second term is the GraphQL programming language. At first glance, GraphQL may look to be a programming language created by the Graph. You may be surprised to learn, however, that it was instead created by Facebook back in 2012. It is a language for querying data and was originally used by Facebook to gather data for a user's newsfeed before being made public in 2015. The final term to be familiarized with is subgraphs. Subgraphs extract data from blockchains, processes it, and stores it so that it can be easily queried by GraphQL. The component of the subgraph that holds information on the subgraph's data sources, templates, and other characteristics is known as the subgraph manifest. These 3 components work together behind the scenes to extract information from blockchains. Developers build and publish APIs, called subgraphs, that perform queries over the GraphQL. It's also important to understand the key roles of the Graph network, beginning with the indexers. Indexers are node operators in the network that provide indexing and query processing services by staking Graph tokens. For their services, indexers can earn query fees and indexing rewards. Consumers are end users that pay indexers for their services of providing data from subgraphs. Consumers can be web services or any other software connected to the Graph. Next are the curators. Using GRT tokens, curators identify which subgraphs are worth indexing. Curators are rewarded proportionally to the popularity of subgraphs. Curators can be either end users that find particular subgraphs valuable and worth indexing, or developers that would like to see their subgraphs indexed by indexers. Delegators also have a key role in the network. Delegators earn a portion of indexers' rewards and fees by staking their GRT tokens on behalf of indexers. Unlike indexers, delegators don't have to run graph nodes. The last two key roles are those of fishermen and arbitrators. Fishermen verify the accuracy of the network's response to queries, while arbitrators can determine if an indexer is malicious or not. Now that you've got these terms and roles under your belt, let's take a look at a use case example involving popular NFTs. The graph makes it possible to query data from blockchains that is difficult to query directly. Take popular NFTs from the Bored Ape Yacht Club collection. Bored Ape Yacht Club NFTs store their data on the Ethereum blockchain. Read operations are programmed directly into smart contracts, and some basic data, such as owner's address, are easy enough to retrieve. More advanced queries and operations like aggregation, search relationships, and non-trivial filtering are not possible, however. For example, if one wanted to query for all the apes owned by a certain address, and then filter down by one or two characteristics, one would not be able to accomplish this by interacting with the contract itself. Without the use of the graph, there would essentially be three options. The first would be to process every single transfer event ever emitted, read the metadata, and then aggregate it. For a decentralized application to perform this task, even for what would seem to be a very simple query, could take hours or even days to accomplish. Another option would be to build out a server, process transactions, save them to a database, and then build an API endpoint on top of it to query the data. This option would require a lot of time, resources, and maintenance, and also open up exposure to a lot of vulnerabilities associated with centralized solutions. It would be a centralized point of failure, susceptible to hacks. The process can be further complicated due to blockchain properties such as finality and chain reorganizations. The third option would be to use a web-based solution. As we mentioned earlier, Etherscan is a popular alternative to the graph, but is not truly decentralized, and as a result, it is a single point of failure that is open to attacks. As a centralized solution, it does not adhere to the decentralized nature of blockchains in the same way that the graph does. And that's all that we have for today's video. We hope you got a good understanding of the graph and the unique problem it is set out to solve. If you enjoyed the video, please give it a like and be sure to subscribe to our channel. Thanks for watching, and we'll catch you in the next video.